Hello, we are going to cover the topic of sorting and specifically bubble sort. We're going to break this down to two videos. The first one is just talk about the concept, the idea of how to do it, and then the second video we will talk about how to actually do it in the code. Okay. So what is sorting? Now, we've talked about collections of things, right? We study lists, we study sort of arrays, and then we study stacks. So once we have a collection of things, there are a lot of interesting things we can do with the collection. One of the most frequent operation is to sort the collection, and sorting things have a lot of advantages, right? It's easy to find something if they're sorted, right? I mean, usually, let's say a list of names, we sort it by last name. So sorting is good to find information quickly. Now, so sorting is really, it has been very well studied in computer science, probably the most well studied topic in computer science. And there are many different sorting algorithms that have been developed over time and analyzed in excruciating details. And for those algorithms, if you remember, algorithm is just a way of doing things, how to solve problems, right? So like I said, there are many different sorting algorithms. There's bubble sort, other names such as shell sort, heap sort, merge sort, quick sort, and all sorts of things. One of the easiest one to understand is bubble sort, and that's what we'll study in CS3A. Other sorting algorithms that's in one, sorry, 1C, 3C. Okay, yeah. So the reason we talk about bubble sort, like I said, is one of the easiest to understand, but it's also the slowest. But anyway, we have to start from somewhere, and we start with bubble sort. Now, uh, the thing about sorting is usually you have to specify two things about sorting. Is what are you sorting by? Like the example I just gave is, we can sort by last name or we can sort by first name, right? So you have to tell it what are we sorting by, and then what order are we sorting by, right? Are we sorting by ascending or descending? Ascending basically means, 1, 2, 3, 4, 5. Descending means going the other way, 5, 4, 3, 2, 1. Okay. All right, so bubble sort, how does it work? The idea of bubble sort, like I said, is fairly simple. What it's trying to do is it's trying to do this in many rounds, and each round, well, actually, in the first round, it would find the largest one in the list, and then move it to kind of the top or the end, depends on how you look at it. And so that's why it's called bubble, right? It bubbles the largest to the top. That's in the first round, and then in the second round, it would bubble the second largest, not all the way to the top, but because the top is already occupied by the largest, right? So we'll move the second largest to the one right before the top or right below the top, depends on whether you're looking this vertically or horizontally, right? And then you repeat that. You find the third largest, and then move it right before the second largest, and so on and so forth until everything is sorted. So that's kind of basically the idea. So let's look at an example and see how it works. And in this example, we are sorting integers. Oh, it's not an array. I'm sorry. I need to change that. Not an array. We're sorting a list of integers in the ascending order. So at the end of the day, we want the smallest one to be at the beginning and the largest to be at the end. Okay, so how do we move largest to the end? So what we actually do is that we compare the integers pair by pair. Okay, starting on the left side and move on the right. And we'll swap them if they are out of order. Okay, so let's look at this the first time. So we're starting with round 0. Okay, We look at 7 and 99. Well, they are in order because 7 is less than 99, so no need to do anything, right? They are already fine. The next pair, we compare 99 and 18. Well, 18 is less than 99, so we should swap them, right? So we swap them, and then we look at the third pair, 99 with 30. And again, 30 is less than 99, so 30 should come before 99, or we move 99 further to the right. So we have to swap them. Okay, and then finally, the last pair we compare is 99 with 5. And again, 99 is bigger, so it should go to the right side of 5. So we swap them. And there we've done one round, and look at the effect of what happens at the end of this round. We move the largest of the entire list, 99, all the way to the end where we want it to be, right? Is the rest of the list, is it sorted? Well, not quite, right? Not quite. Things are still out of order, but we move the largest to the end. Okay, so we have to repeat now. We have to do the whole, have to start the whole process over. So we compare 7 and 18. Well, they are in order, no need to swap. We compare 18 with 30. Well, they're again in order, so it's fine. And then finally, we compare 30 with 5. And, well, they are out of order, so we swap them around. Okay. Now, based on what we did before, we should do one more comparison. That, we should compare 30 with 99, and they're in order, so there's no need to swap them. That's fine. However, is this last last comparison of these last two numbers, is it necessary? Well, it's not, because in the previous round, in round 0, we already moved the largest, which is 99, all the way to the end. So we know once we at the second round, we don't have to touch the last one, because the last one is already the largest and it's in the right place. So we don't need to do this. We don't need to do the last comparison. And this process of not having to do something to make things faster, it's called optimization. So it's just a way of doing the same thing, either faster or doing it with less resource. Okay, but do we have to do this optimization? Well, we don't. As we already see, we'll do the actual work and figure we don't need to swap them, and we don't swap them, right? So optimization is something that is not required for the correctness, but it should help to make things faster, or again or do the same thing with less overhead or less resource. So this is optimization number 1. Okay, now so we that's the end of round 1. So let's look at round 2. Round 2, again, we compare 7 and 18, and okay, well, no need to swap them. They are in order. We compare 18 and 5. Well, now they're out of order, and we swap them, right? Now, the question then is, okay, do we need to compare 18 and 30? Well, we don't, because 30 is the second largest, and in the last round, it was already put in the right place. So this is, again, applying optimization technique number 1, because we can stop, because we know, the last 2 are already in the right place. Okay, so now we do this again. Round 3, or the 4th time we're doing this. Remember, we start the round number at 0. So round 3 is the fourth round. So we're comparing 7 and 5. they are out of order, so we have to swap them, 5 and 7. And once we swap this, wait a second, let me try to think. Yeah, once we swap these, do we need to keep going? Well, we don't, because in the previous round, we're already putting the last 3 in the right place. So we can really kind of stop this round already. Okay. Now, there is actually a second kind of optimization that we can do here. And you maybe try to think about that. I mean, do we need to keep going in this case? Well, turns out we don't, right? Because at this point, if you look at the whole list, everything's already sorted. So we don't need to look at the pair. We just look at again. It's done. Now, so in this example is actually slightly less obvious what optimization number 2 really is. So let's look at a better example. So if you look at this list, 1, 2, 3, 4, 5. Right at the beginning, we don't know if they're sorted or not. So we'll go through it pair by pair. You know, we compare 1 and 2, 2 and 3, 3 and 4, 4 and 5. What happens at every single one of these swaps? Well, or sorry, not every single one of the swap, every single one of these comparisons. Well, it turns out for all of these comparisons, it tells us we don't need to swap anything, right? All of them, each pair, each of these 4 pairs of comparison, we don't need to swap any of them. So when you go through an entire round without swapping, what that tells us is, well, this thing is already sorted. The entire list is already sorted. So, so in that case, we don't need to go through another round at all, because we're done. So we can stop early. So there are 2 optimizations that we can do, but the basic idea is, again, just go through the list, bubble up the largest one, bubble up the second largest one, bubble up the third largest one until everything's done. All right, so that's the end of this video. In the next one, we'll try to put this in code.